Hello everyone, welcome back to my series of trying the Project Euler problems with OpenAI Codex. This is quite a cute problem, so I hope you'll enjoy it. 2520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible with no remainder, by all the numbers from 1 to n? Right, so if we think about this naively, n factorial, if we just take the numbers 1 to n and multiply them all together, that's definitely evenly divisible by all the numbers from 1 to n, because it has them all as an explicit part of the multiplication process. However, that's going to give a very big number, n factorial, and maybe it's possible to create a number which is smaller than that. So for instance, if you have n factorial, and you have 2 and you have 4 in your sequence, then because it's divisible by 4, you don't need to multiply n by the 2, because it's already divisible by 2 because it's divisible by 4. And I note that in the constraints to this problem, it says there'll be up to 10 test cases, but n will only go up to 40. So it's clear that though this is growing slower than n factorial, it's still growing pretty quickly. And so they can't have really large n's because the numbers will just get huge. Okay. So over here in the Codex playground, I've brought in this, and I've written find the smallest number larger than n, which is evenly divisible by all the numbers from 1 to n. So let's see what it does. Okay, so this is a kind of brute force solution that it's come up with. I think it's slightly garbled though. So it says start with I equal to n. Okay, well that's reasonable because it can't be a number smaller than n, because how can a number smaller than n be evenly divisible by n? So it's reasonable to start at n. And then it says while true, add n on, and then check for all the numbers in the range 1 to n, is it divisible? And if it's not, break out and try the next iteration. But else, and again, I'm not quite sure what this else statement is referring to, like there should be an if for an else and there's no if. Then it will print it and it will break and say, okay, I found this, and it will break out of this loop here. So I don't think this will even run, so it's not kind of correct code. Oh. So maybe this else is triggering off this if? That seems really bizarre to me that that works. Anyway. Okay, so it doesn't like it. It says it's got the wrong answer for 2 different test cases. So I think the first problem is, why is this going up in steps of n? I suppose if the number is divisible by n, it must go up in steps of n. So I suppose that is reasonable. But I think the problem is that at the beginning of this loop, the first thing it does is set I equal to n, and the next thing it does is add on n, so the smallest one it will check is 2n. And so I think one of the issues is, what if the solution was n itself? Because you can envision a scenario where n is big enough. So let's try putting that to the n. So we'll say check n first, and only go up if that doesn't work. Okay, so that's fixed it. So that was the problem, is that it was initializing in the incorrect way. So okay, so I'm learning something here, that this is in fact, you know, this program's clearly better at writing code than I am, because it can write things that I think are garbage and it actually works fine. So that's worked completely well. But I think there's a more elegant way of approaching this problem, because this is just in a way, this is very elegant because it's very few lines of code. So it's very straightforward what it's doing, and it's just doing this iterative process. But it may have to check an enormously large number of numbers, right? Because it's iterating through here, it has to go through this thing, and it has to try and find the right amount. So I think there's a more elegant way of doing it, which is to kind of notice. At first I thought it was, if you have some number n, if you find all the prime numbers smaller than or equal to n, then multiply those. Is that the smallest number which will be divisible? Because in some ways, if you think about it, if you have, let's look at some of these examples here. Okay, yeah, so if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if we just did 2 times 3 times 5 times 7, well, that is going to be divisible by 10 because it's got 2 times 5 in it. So we've already got 2 and 5, so we don't need to put 10 in. And again, it's got 2 and 3 in it, So if we multiply 2 and 3, then we've already got 6. So why do we need to have 6? You know, and this kind of thing. So is it just enough to multiply the primes? And I think the answer is it's not. It's actually not quite just the primes, because if you just multiply 2 times 3 times 5 times 7 together, you're not going to be divisible by 4, because 4 is 2 squared, and you kind of want to go the other way. So rather than having 2, 3, 5 and 7, what I want to do is to take each prime and raise it to the highest power I can while it's still under n. So I wanted to use 8 instead of 2, okay, because if it's divisible by 8, then it's definitely divisible by 4 and divisible by 2. And then for 3, I want to use 9 instead. So I want 8 and 9, and then I want 5 and 7. And I think that should be enough, because if it's, let's check it. So if we had 5 times 7 times 8 times 9, and actually, let's multiply that together. 5 times 7 times 8 times 9. And that gives the 2,520, which is the answer, right? And we can check it here as well. So if is that a multiple of 1? Yes. Is that a multiple of 2? Yes, because we put an 8 in, so there's definitely a factor of 2 in there somewhere. Is it a multiple of 3? Yes, because it has 9 in it, so it's a factor of 3. And 4, yes, because that's half of 8. And 5, yes, because we did that explicitly. 6, yes, because it's a multiple of 2 and 3, because it's a multiple of 8 and 9. Okay, so it is a multiple of 6. We put 7 in explicitly, we put 8 in explicitly, 9 explicitly, and then 10 because it's 5 and 2. Okay, so how do we get OpenAI to solve it like that? Like, that is kind of complicated. Right. So I think maybe we should break this down into a few steps. So we'll say, first, make a list of all the prime numbers less than or equal to n. Because if n is a prime number, then it should be included. Okay, wow. So this is creating a prime sieve, the sieve of Eratosthenes. We talked about this quite a lot a couple of episodes ago. It's interesting that this is clearly just taking from someone's code base. Like, you can see how the program's been trained, that when it comes across this idea, it's just going to take that. And actually, it's quite interesting. Eratosthenes is a really interesting character, so maybe let's just have a quick historical diversion. So the sieve of Eratosthenes, what you do is you take all these numbers, and then you say, okay, 2 is the first prime number, so delete all of these other ones which are multiples of 2. And then take 3 as the next prime number, because it hasn't been deleted yet, and delete all the multiples of 3. And then delete all the multiples of 5, delete all the multiples of 7, and you sort of sieve out all the things which are remaining. And you only have to go up to the square root, so once it's got to 10, you know you've sieved out all of them, because there's no way, like, yeah, going up to the square root is sufficient. I think. Maybe I've got that completely wrong. Actually, no, because when you no, sorry, that's complete rubbish. Because when you have 17, you're going to need to sieve out 34. Oh, but that's even. I'm sorry, I'm talking nonsense here. Okay, yes, going up to the square root is sufficient, because say you take some number like 17, the number, if you have some other composite which is a multiple of 17 in here, like 34 for instance, that's 2 times 17. And whatever you're multiplying 17 by to get something in this range will be lower than the square root already, which means it's already been checked, which means it's already been sieved. And Eratosthenes is a really interesting character. Let's see if we can find... Eratosthenes of Cyrene. Looks like this. It kind of looks like Socrates, I think. But yeah, 276 BC to 195 BC, so a long time ago. But he managed to compute the circumference of the Earth, and he used it by using 2 sticks to measure shadows at different times of day, and he got it within 10% of its actual modern number, depending on, here we go. So he had 2 sticks at different times of day, and he measured the angle and the distance between them, and using that he was able to work out the circumference of the Earth. And no one quite knows the conversion of stadia, which is an ancient Roman measure of a mile, to modern miles, so we're not exactly sure how much it was, but yeah, there we go, with an error between 2.4% and 0.8 of the circumference of the Earth, which is just a staggering achievement for someone so ancient, and also a very good counter-argument to people who say, oh, everyone in the past used to think the Earth was flat. Well, Eratosthenes in 200 BC, he knew the Earth was spherical, and he knew the circumference of it, or oblate spheroid, I think they call it. And then again in 1300, Dante's Divine Comedy is all about the sphere of the earth. And when Christopher Columbus set off to go to the Indies, he set off west because he knew the earth was a sphere, and so he was trying to go west all the way round to get to the Indies. He'd actually miscalculated the size of the earth and thought it was much smaller than it was. And actually, if he hadn't bumped into America, his entire crew would have died of starvation because there's no way you could have made it all the way across the Pacific with the resources they had. So no one's ever really thought the earth was flat, no one particularly serious for a long, long time. So that's a bit frustrating. So that's a huge digression, but I'm hopeful. Yeah, there we go. So it's interesting again, this is some prime list algorithm. So it says go from 2 to n and then check divisible. I think that should be fine. And then it's got some other problem that it's solving here. Find a list of integers equal to n that have 3 divisors. So maybe this will come up later, I don't know. Maybe this is a Project Euler problem. Okay, so, and let's just print this prime list and check it's doing it properly. This is good. Good coding practice, just to make sure that it's, you want to check your work. So it says the primes less than or equal to 3 are 2 and 3, and the primes less than or equal to 10 are 2, 3, 5, and 7. Okay, so that's pretty good. Right, so now we have those primes. Now this is quite a complicated instruction of so what we want to do is for each prime in the list, raise it to the highest power you can, so it is still less than n, and then append it to a new list. Okay, I wonder if it can handle that, because that's actually quite a complicated instruction. But what I'm saying is, I don't want 2 in my list of factors, I want 8. I want 2 cubed, so I want you to keep raising it to powers until it's, but while it's still smaller than n. And let's see if, okay, so prime list 2. Okay, we don't want to do this. For I in prime list, j equals 2, while I to the power of j is less than or equal to n. Okay, so this isn't quite right, because it's going to say append it every time, but okay, let's give it another go. Let's keep, come on OpenAI. I've given you a really complicated instruction. Let's see. Okay, it's renamed it. It said prime list raised. For I in prime list, okay, so it's got the I in prime list. Power equals 1. While I to the power is less than or equal to n. Okay, so the problem is that if I to the power, it's going to raise it to a list, okay, and then it's not got the sort of and then. So let's keep trying. Let's keep digging around with this. For each prime in the list, find, raise, let's see if it likes that better, if it sort of gives it 2 instructions. Oh, okay, so it's kept going. I don't think we want any of this. So prime list raised. For I in prime list, while I is less than n, yeah, again, it's trying to append it too soon. It's going to append 2, 4, 8, and so forth. It's collecting all of them. And again, why is this I times I? Okay, no, that is reasonable. So I might help it by hand, I don't know. I'll give it one more chance, and if not, I'll help it by hand. Prime list raised append. Okay, so this is saying take n and divide it by I, and then raise to that power as an integer. So if I had 10, if n was 10, this would divide by, say, 2 and come up with 5, and I to the 5th power. No, that's definitely too big. All right, let's try again. Okay, I don't think that's right at all. Okay, so it's really struggling with this. For I in the prime list, while I is less than or equal to n, multiply I by itself. Okay, so we want to say multiply this up until it's too big. So, and then you will get to this point. Okay. So then we want to do, once that's done, we want to do I divide equals I. Well, actually no, because another problem with this is that when I is growing, this is the first time this multiplies itself by I is going to be 2 squared, but then the next time it's going to be 2 squared times 2 squared, which is 2 to the 4, which skips out 2 cubed. Okay, so for I in prime list, we're going to have power equals what? While I to the power is less than or equal to n, we want to add 1 to the power, right? Then we want to take the last one off because it will have done 1 too many. And then we want to append I to the power to prime list raised. Okay, let's have a go at that then. How are we doing? So we printed out prime list, and now we have prime list raised. So let's print. And again, it's an interesting question of like, is this more elegant or not? Because in some ways we're doing something mathematically deeper, but in other ways I'm spending an awful lot more energy doing it. Okay, so it has done the right thing. We've got 8, 9, 5, and 7, which are the 4 numbers that we wanted to put in, but that's good. Yeah, so that's nice, but it hasn't multiplied them. So then the last step is, so all we need to do is print the product of prime list raised. So just multiply them all together and print the answer. And so I find this a bit surprising. I tried this earlier and I can't actually get it to do this, which is kind of fascinating. Like, you know, you would think print the product of a list is not a hugely complicated thing, but it's saying print the list and then print the list, the last element of the list, or reduce. You see, that might work. That I don't know exactly what that is doing, but it might work. Let's see. Fingers crossed, it may have done it. Again, this is a good example. Yeah, reduce not defined. I'm guessing that's from a library, maybe. Okay, and that's another problem is, if it finds code from a library, how does it know what to do? Okay, multiply all the elements of prime list raised and print the result. See, again, it wants to do the sum. That's not right. We want the product. So I think this is a good, the question of what are the limitations of Codex. It can't seem to solve this problem of multiply the elements of a list together and print it. It doesn't seem to know how to do that. So let me have a go. Let's have answer equals 1 for p in prime list raised. Answer times equals p, print answer. Okay, test case 1, all test cases, done. Okay, so interesting discussion point, right? Which is more elegant? The first solution, which was really straightforward, or this one? My guess would be if n gets really, really large, maybe this is better. I mean, computing the primes less than n is an enormous amount of work, but I think probably less work than iterating through above n and checking over and over again whether you've got divisors there. So I think that's probably better, but I'm really not sure what the order of this is in terms of computer science formalism. Okay, I hope that was interesting. Quite a cool problem, I thought. Like, I thought it's only problem number 5, but there's actually a little bit of subtlety there in how to get this nice solution out of it. So yeah, I hope that was cool. Hope you enjoyed it. See you in the next one.